Okay.
That'd be okay.
So I'll switch to English now because I don't know most of the words in Turkish anymore with some of the scientific words essentially. So what I'll try to do today, this afternoon, is to try to give you a brief idea or a brief summary of what Community Earth System Model is, CESM, that's CESM. And I'm currently serving as the chief scientist, and I'm in my third year, I think, being chief scientist, and I have about another year to go. So what I wanted to do is first, just to make sure that everybody's on the same page, briefly introduce CESM, starting with the global sort of coupled modeling. Then I'll sort of summarize our efforts in our participation to coupled model into comparison project, phase 6, that's CMIP 6. I'll show some highlights, summaries from our latest CESM simulations. That's the second version of CESM, CESM2. Then I would like to briefly mention a few other activities and projects that I think might be of interest to you. And all of I should also mention, and I'll come back to it at the end as well, that all of our model versions and many of our data sets are freely available for any analysis that you guys you may be interested in. So this is very basic, and I'm pretty sure everybody in the audience knows about this thing, but I just wanted to make sure that, just to clarify what we are doing, we are essentially creating a model to simulate the global Earth system. And these models, as many of you know, use physical equations to simulate key fields and processes in various components. And some of them are listed here: atmosphere, ocean, land, sea ice, land ice, and we have also waves in our coupled system. And by necessity and lack of resources, computational resources, primarily our resolutions are coarse. Most of the models participating in the CMIP 6 effort, or for IPCC purposes, they tend to use order 1 degree nominal resolution. Some of the participants use quarter degree, but generally many of the processes are below the grid resolution, and they need to be parameterized, and that's usually done in terms of the explicitly resolved variables in the model. And those processes, when I say parameterized, they're essentially parameterized building on our understanding of processes, either based on observations, that's very limited, however, or highly detailed either process models or large eddy simulations. So we try to learn from them for the processes that are not being resolved in the coarse resolution models, then they are essentially parameterized. And CESM is one such model. And I just put a schematic down here. At the center, I mean, it's not the center of the universe, but at the center, let's say we have a coupler, and it provides communication between the various component models. We have the atmospheric model, and in our case, that's a community atmosphere model. We have both a low-top version, that's our standard workhorse model, and also a high-top with more comprehensive chemistry version of the atmosphere. We have a sea ice model, land ice, and that's for glacials, and I'll show you an example of that. Our ocean model, which includes also marine biogeochemistry. We have waves represented. We have a runoff model, and we have the land model, which also includes land biogeochemistry. So it's one of the more comprehensive and complicated climate models. And one of the unique things about CESM is that C in it, in the name, it is truly a community model. We collaborate a lot with the community, particularly the US university community and many other national labs in the US. And the forcings, for example, when we want to simulate the climate, the greenhouse gases, anthropogenic aerosols, volcanic eruptions, and solar variability, and as such, they're essentially incorporated in the atmosphere. Another external forcing can be within the ocean model, that's the geothermal heating. We do not, even though we have the capability in the model, we do not essentially use geothermal heating in the model. So just to give you a brief idea about the demand on or demands on resources when we run these coupled climate simulations, I have this sort of simple schematic here. It is generally a war between sort of complexity, ensemble size, and resolution needed for these climate models. And the top two panels show sort of the evolution of the coupled models. And starting in sort of mid-60s or so, when people talked about coupled models, it was primarily AGCMs, right? It wasn't even coupled. Then they started to add an active ocean model, and it was just a two-component system, and that was called the coupled system in essence. But as you can see from this schematic, in fact, I was asked to essentially update this panel here, which I haven't done yet, with the additional complexities. Over time, more and more components got added into the climate system, such as ice sheets, biochemical cycles. We have now interactive vegetation and all that stuff. So this area is essentially increasing continuously. And not only we are adding more component models, but we are also adding more complexity within each component model. For example, if you take the ocean and sea ice, initially they were really simple models, but we keep adding more parameterizations and more features into those models, and their complexities are also increasing. More and more recently, people are realizing that in order to get robust estimates of what's going on even with the climate, let alone weather time scale, we need to have essentially quite a few ensemble members per sort of case. And what I mean by that, in the past, when people ran transient or historical simulations for the 1850 to 2100 period, usually only one member was run. But now people are realizing that in order to get a better estimate of what's going to happen, you need at least minimum of 10, but now we are going towards 40 ensemble members. And of course, here we have the resolution, demands on resolution. This is sort of T42, and these are spectral truncation for the atmospheric model. This is T40 order 3 to 4 degree resolution. T85 is more like order, I believe, 1.8 degrees or something like that. So depending upon what your interest is, you may need to consider higher and higher resolution, perhaps, particularly for informational regional scales. But all of these also put significant demands on your available resources. The bottom line is that in order to be able to sort of set up your case in a coupled system, you need to essentially sort of decide up front what science you're after, and then that'll determine essentially what features that you need to use in the model, how many ensemble members you will need, and what spatial resolution essentially you may need. And of course, availability of computer resources is another issue, and I'll touch on that thing towards the end of the presentation. So, just to come back to CESM, CESM has been actually, it was previously named the Community Climate System Model. We changed the name to CESM to put Earth into the name. We have been around for about 25 years, essentially, so that much experience. And CESM is a bottom-up sort of system. As I said, community is quite important, and we have 12 working groups, and this Earth System Prediction is a very new working group. It was just formed a few months ago, and all of the work, all of the ideas essentially occur and come from these working groups. And at the top, we have a scientific steering committee, and we have an advisory board. Essentially, scientific steering committees essentially makes decisions on sort of important sort of model configurations and what major activities of CESM should be. Most working groups have winter and spring meetings. In addition, they also meet during the annual workshop. This year, unfortunately, due to the virus, we are going to hold our workshop, annual workshop in digital format, and it is during the week, 15th through 17th of June. And so far, I believe we have close to 500 registrants for that workshop, and it's going to be through Zoom. CESM can support a wide, quite a big range of climate science goals through a single model code base. We have single column, very coarse resolution versions of the model, and that can be used for physics development. An example can be, for example, vertical mixing developments within the ocean model in a single column mode. It can be used at lower resolutions. We have versions anywhere order 4 degrees, I believe, to 2 degrees in the atmosphere, and order 1 degree. We tend to use 1 degree regardless in the ocean model, but they can be used for essentially much longer simulations, for paleo timescale simulations. And at the high end, we have high resolution versions of the model. In fact, we are working on right now so-called cloud permitting, order 4 to 5 kilometer resolution in the atmosphere, and similarly 5 kilometer resolution in the ocean model. And also our nominal 1 degree horizontal resolution version of the model can be classified here too. That's used for CMIP purposes. Within a single framework, and we are trying to get more into this, essentially, we have many code bases that can be, or many code combinations, many component combinations that can be supported. We can, in our fully coupled version of the model, all of the components are active, but that doesn't have to be the case. You can run in a mix and match mode. You can replace some of the models with so-called data models. They essentially read data sets. And an example of that is so-called ocean-only or ocean sea ice coupled simulations. I don't know whether you heard of core simulations, coordinated ocean ice reference experiments. They essentially use active ocean and sea ice models, but the atmospheric model essentially is not active. It just reads in reanalysis data sets to force the ice ocean components. We have several simplified, so-called simplified model configurations, such as aquaplanet. You can, in the atmosphere, we have the SE dicore, that's a spectral element, finite volume dynamical core. You can still use spectral truncation, spectral dynamical core, and then we have the so-called, we are putting in MPAS dynamical core. That's the model for prediction across scales. Each component model contains numerous options, numerous parameterizations, and we are essentially continuously increasing number of supported component sets and configurations. So it's a very comprehensive, I would call also a bit complicated modeling system. It can also run on the cloud, but it can also run on the laptops. We have the Atmospheric Model Working Group essentially created a Docker container version of CESM2, particularly focusing on the atmospheric component, single column atmosphere. So they are being used. These simple models are being used in various tutorials that we offer. And there's going to be another tutorial this year, but unfortunately that's going to be virtual as well. So so that was sort of a very brief introduction to some of the capabilities of CESM. And I'll just now focus on a little bit our efforts towards CMIP 6. And just to give you a brief idea about what CMIP 6 is, or what CMIPs are, participation in CMIP requires running quite a lot of simulations. And the chart here, or the schematic on the right side here, shows sort of what is sort of entry-level participation. In order to participate, centers for most of the MIPS must perform longish order 500-year pre-industrial control simulation, a 1% CO2 concentration increase simulation, quadrupling of CO2 simulation, and AMIP style simulations. AMIP is simply atmospheric model intercomparison project, and you just run the atmospheric model by subject to observed SSTs essentially. And these 4 sets constitute so-called DEC simulations. That stands for Diagnostic Evaluation and Characterization of Clima. Klima is Climate for German, and Bjorn Stevens was responsible for this acronym. And that is supposed to be independent of a CMIP version. As you can see here, that deck doesn't have a number attached to it, and it can be up to CMIP infinity, but it's supposed to be a similar set of experiments. Then on the left side here is the sort of wheel of fortune. Deck is at the center. We have the historical simulations shown by gray here, and around it there are broad scientific questions, range systematic biases, variability, and response to forcing. And around that there are more specific sort of topic areas. And finally, at the outer edge, you can see some of the so-called endorsed model into comparison projects, various MIPs. And all of these red MIPs, and we added quite a few, 3-4 additional ones, are the ones that CESM is participating. And in CESM, we are participating with 2 sets of simulations. Our workhorse model has 1 degree nominal resolution. We have run both with the low top Chem 6 and high top with comprehensive chemistry versions. That's the vacuum, whole atmosphere chemistry climate model. So we have all those sets. And then in order to essentially serve sort of the university community and paleoclimate community, we also created a 2 degree version for the atmospheric model, which is a lot cheaper. Just to give you an idea, vacuum one, with high top with comprehensive chemistry, takes about 30,000 hours on our Cheyenne computer just for 1 year. In comparison, Chem 6 is about 8 to 10 times cheaper. It's about 3,500 CPU hours for 1 year of simulation. And 2 degree versions are about 50% cheaper than those numbers. All of these new simulations are run with CESM2. That's the new version of the model. It was released back in December. Actually, it was released in summer of 2018. Since then, we have been doing incremental releases. These are essentially adding more features to the model or more component sets. They are not changing answers, but you can run many of the DEC and CMIP simulations out of the box. We are going to release another version towards the end of July, and that's going to be CESM 2.2. That's going to be answer changing, and it's going to include additional features, essentially, additional developments since summer of 2018. If you're interested in looking at some of the analysis, we have essentially arranged for an AGU CESM2 virtual special issue. And we are also providing these manuscripts from our own website, and that's given here. And we are anticipating more than 70 total manuscripts, and we are about halfway there. So far, 35 plus manuscripts either have been already published or submitted. The deadline is, again, June 30th, but you may have heard it, IPCC deadline just got extended by 4 months, so I may essentially push this deadline a little bit. And if you're interested in the sort of the broader summary of CESM2, an overview is provided in this paper that I was the lead author. Okay, just a few highlights. One of the sort of challenging things with our new model was duplication or representation of the surface temperature, surface air temperature time series during the 20th century. And what is shown here is the temperature anomaly, and this is for the entire global area. And from the 1850 to sort of the end of the CMIP period, that's the 2014, end of 2014. And when we put the model together, one of the biggest challenges that we had, atmospheric model includes a new parameterization for the clouds, CLUD. We are also including the aerosol indirect effects, and we also switched to CMIP6 forcing. And in many of our initial simulations, we got this green line here as representing temperature evolution during the 20th century. And you can see that we ended up getting cooling. at the end of the 20th century with respect to the baseline period of 1850 to 1870. And you can see the observational or the analysis estimates are given by these three estimates, grayish lines, and we need to get this warming. And after quite a few trials, and after essentially tuning of the club parameterization with respect to, again, as I said, some of the process studies and observationally based analysis, we ended up at the end with the warming that we see in the red line here. That's the CESM2 CAM6 simulation. 10 ensemble member spread is given by the pink line here, or pink shading there here. We have 3 ensemble members for vacuum. It's an expensive simulation. I just show the ensemble mean here. And CESM1 is the older model version that's shown by the dashed line. At the end, I mean, we are not after capturing every single wiggle in the observations, but overall, we are capturing the evolution of the surface air temperature during the 20th century. One of the big improvements or significant improvements is essentially happen in precipitation in the new simulations. What I'm showing here is the GPCP observations for this period given here. CAM6, VACUM6, and the older version of CESM are shown here as the bottom set of plots. These are all ensemble means, by the way. And then the right side shows their differences from the GPCP observational estimate. So one thing that we found out in these simulations, whether we use low top or high top with comprehensive chemistry, many of the properties that we look at, precipitation, surface air temperature, they are very similar. You can see it right here in the difference distributions. We are also seeing that if you look at either the RMS or the mean values, we are seeing improvements in the precipitation compared to the older version of CESM, and that's primarily occurring in the low latitudes, tropical and equatorial regions. You can see improvement in the SPCC, South Pacific Convergence Zone in the new simulations, and also there are improvements in the Atlantic and Indian basins as well. Another big improvement that we have seen in the simulations that our atmospheric people were quite happy is the representation of the shortwave cloud forcing. And the analysis/observational data set is here from series for the 2000-2013 average. And these plots, the remaining plots, show differences of model from this estimate. This is from CAM6, this is from VACUM6, and this is from LENS, the older CESM1. And you can look at either the mean values or the RMS in particular. You can see big improvements. I mean, CESM, the older version of the model, was reflecting too much. And that has been essentially eliminated quite significantly, particularly at low latitudes. And our atmospheric folks are telling us that it's mostly associated with new or better updated microphysics and better representation of low clouds via the club parameterization. Another improvement occurred in the representation of the Madden-Julian oscillation. This is, so again, I'm using the same format in these plots. This is the reanalysis estimate, and the others are showing the CESM2 vacuum with CAM6. This is with VACUM6, and this is CESM1, the older version of the model. So in these plots, what is shown here is that the precipitation anomalies are shown with the color here, blue and the red colors, and the contours are showing the 850 millibar zonal wind anomalies. So you can see a clear propagation of these both wind and precipitation anomalies in eastward direction in the reanalysis product, which is quite nicely captured in both of the low top and high top model versions. And you can see that these two new simulations represent significant improvements over what we had before. In fact, if you look at the CESM1, we were seeing actually an anomaly propagation in the Indian basin in the wrong direction. So atmospheric modelers were quite pleased to see these improvements. This is just to show you what we are getting in terms of ENSO. In one of the big things that we have done in CESM1 was to improve ENSO compared to our previous model versions. It was pretty bad in our previous versions. And in CESM1, we spent quite a bit of time improving actual model physics, and there is no silver bullet what actually changes the ENSO amplitude or frequency, but at the end, we managed to get a decent representation of ENSO. By the way, these plots are in the color is showing the ENSO El Nino minus La Nina anomalies in temperature, and then the contour plots are the sea level pressure imposed on top of it associated with these anomalies. Observations are given here. Maybe it's misleading, observations / reanalysis here. Chem 6, low top, high top, vacuum 6 here, and now it's the CSM1. So we are retaining more or less what we got in terms of the SST anomalies with respect to ENSO. In the low top version, our amplitude is a bit on the high side, but many of our variability folks were quite excited to see this tilt of the low pressure anomaly to the west of the North American continent. And it is essentially impacting what happens over the North America in terms of temperature anomalies. That tilt is captured in CSM2 simulations, both of them, but it is not so well captured in CSM1. So this is apparently improving many other ENSO teleconnections, capturing those details. Greenland, so as I said, we have a land ice model in the simulations. And what is shown here is the Greenland surface mass balance. They do not have any, they do not have any sort of Greenland scale observations. So what the community, in that community, what is used is sort of a very high resolution regional simulation of Greenland ice sheets. So that's acronym is RACMO. I can't remember exactly what it stands for, but that's what that model produces. This one, in the interest of sort of reducing complexity, is showing the low top version, but the high top is very similar, is showing what we get in our CSM2 CAM6 simulation. So you can see quite a nice agreement in spatial structure of what we should be getting in terms of the surface mass balance. This is showing now, the right plot shows the time series of surface mass balance components from 1850 to 2014, precipitation, melt, refreeze, runoff, and the total is given down here, and the scales are actually going from, is alternating between left and the right of the plot. And the so-called sort of the truth coming from RACMO are shown by the, truth is shown by the dotted line, black lines here. So there's apparently so-called breakpoint in surface mass balance, and that's essentially indicated by this sort of decline of the surface mass balance right here. Hopefully you can see my arrow hopefully here. And our land ice guys were quite happy to see some kind of breakpoint. It is, you can see some kind of a reduction in the surface mass balance. Although, if you look at it, in the RACMO simulations, that's mostly associated with precipitation. In our own simulations, that's a combination of essentially, you don't see much of a decline perhaps in precipitation, but all of the other components conspire to get some kind of a breakpoint here. And land models, land model folks actually developed quite comprehensive features in the land component, and they also developed new diagnostic tools. This is called ILAM. You may have heard of this thing. It is actually including quite comprehensive set of summary diagnostics for many land features. So in this plot, reddish colors or orangish colors are bad. Greenish colors are good. So you can see that CSM1, old simulations, and in CSM2, 3 ensemble members shown here, many things are essentially in the yellow region. There are a few exceptions. One of the more important things here is that this relationships, That's quite important. It is essentially indicating physical relationships, causal relationships between two things like burned area and precipitation. In the older model of the older version of the land model, these were all red, reddish colors or orangish colors. In other words, these two relationships, known relationships between burned area and precipitation, for example, were not captured properly. In the new model simulations, these are green. So that's actually, the model is doing the right thing in a sense. And one of the important things, emerging properties of the climate system or these simulations is the so-called equilibrium climate sensitivity. And you may have heard of this thing by now. Many of the newer versions of the coupled models are showing larger equilibrium climate sensitivity. For those of you who do not know what equilibrium climate sensitivity is, it is a surface air temperature, change in surface air temperature or surface temperature at equilibrium at CO2 doubling. And this is an unattainable quantity in a sense because we never run these simulations to equilibrium. And these are estimated from relatively short, order 150 to 200 year coupled simulations in which CO2 is either doubled or quadrupled, or you can estimate them from these numbers from simply from slab ocean models. And I put the CESM1 older model version. We used to get about 4 degrees. In the new model versions, we are in excess of 5 degrees. This is a plot from Jeremy's paper in review. It is showing equilibrium climate sensitivity as a function of transient climate response. Transient climate response is, in my view, something more useful because you take your coupled case, you increase your CO2 concentration at 1% per year level up to the doubling of CO2, and you look at the change in surface air temperature. So 2 CESM simulations are given here, and we are not alone in our representation of the higher value of equilibrium climate sensitivity. Many of the models are now showing equilibrium climate sensitivity well in excess of 4.5 degrees. In the previous CMF5, we had very few models with 4.5 or higher. I don't recall actually having anything above 4.5, but anyway, you can see that now many centers are reporting quite high equilibrium climate sensitivity values. And from CESM perspective, we are getting, it is not a single, again, silver bullet. We are finding that it is due to this increase is due to accumulation of relatively small changes, particularly associated with the clouds. And particularly what's happening over the Southern Ocean with clouds seems to be impacting this high climate sensitivity. But the point here, another point that I want to make here is that even though our climate sensitivity is high, our TCR, transient climate response, is the same as before. That did not change at all. It's a matter of time scales, I guess. And just final summary plots. These are from John Fasulo, again from NCAR. He developed new tools, a so-called climate model analysis toolkit, and it essentially evaluates coupled model outputs from many coupling modeling centers using order 30 atmospheric variables, also looking at their seasonal cycle, and so is included water energy budgets, and it assigns sort of a quality value, correlation value, sort of pattern, the mean pattern correlation value. In this plot, red numbers are good, blue numbers are bad, and green is sort of in between. So more you are towards the left side of this plot, your model is better. So the reason I'm showing it, of course, I'm biased. You can see that this is about a month and a half to 2 months old. And at that time, he used 3 ensemble members from submitted, the solutions submitted to ESGF. And you can see that the top 3 are CESM, low top, And then the vacuum ones are the high-top atmospheric model version. I mean, you can see that all CESM simulations seem to be within the top 10 easily in many of these metrics. Okay, so I would like to now spend a few minutes on a few other activities and projects that are going on with CESM, just to give you a flavor of what we are doing. So this version of CESM also has variable resolution capabilities. In this case, the previous versions of the model that I showed results from, they are with the finite volume dynamical core in the atmosphere, but we also have the spectral element dynamical core. And it is with that dynamical core, we can essentially do grid refinement in regions of interest. And in this case, this is the CONUS region, that's the continental United States version. And you can see order quarter degree resolution, not quarter degree, 14 kilometer resolution over the continental United States, gradually increasing to 1 kilometer resolution elsewhere. And we are using this, we have versions over the Arctic Ocean as well. And this is just showing a simulation of ozone. The top panel is the standard 1 degree simulation. And the bottom panel shows the 14 kilometer resolution over the continental US. And our chemistry folks were quite happy to get these regional details using this particular model version. By the way, I should mention that spectral element model version is also the atmospheric model version we use for our high resolution applications because it simply scales better on high processor counts. Another data set that we have available to the community is our large ensemble simulation data sets. And by a large ensemble, this is the CESM1 older model version. We mean order 40 plus ensemble members. And when I was showing that initial schematic in terms of ensemble size, and I wanted to give you an example here, considering so-called Atlantic multidecadal variability. This is something that I work on, AMV. Atlantic multidecadal variability is, for those of you who do not know what it is representing low frequency multidecadal variability of the North Atlantic surface temperatures. And these plots show the regressions of that AMV index, North Atlantic average SST AMV index, onto the SST time series. These top 4 panels from left to this point are observation / reanalysis. And then the remaining plots, I'm just showing only 20 ensemble members here. They show ensemble member representation of this regression. And even though many of them have, I mean, that's by definition almost, have the positive Atlantic SSTs, you can see that in other basins, you get quite different, like if you look at number 14 versus 13, well, this is showing colder SST anomalies, this is showing positive, warmer SST anomalies. So I think in order to get robust results, we need to look at quite a few additional ensemble members. By the way, in this case, the ensemble members were generated by round-off level perturbations of the atmospheric initial potential temperature state in their 16th digit. And then if you run the model long enough, you get quite a few differences. Right now, we are actually collaborating with Busan to create our next CESM2 large ensemble. It's a new collaboration, partnership with the Institute for Basic Science, Center for Climate Physics in Busan. We'll be running now 100 ensemble members. And in fact, this started in January. And we are anticipating that it will be completed later next month or probably in August. As of today, I believe we have completed about 40 of the simulations. And these are covering from 1850 to 2100. Again, these are going to be available to the broad community. Another data product that we have that I'm quite involved with is the CESM large ensemble, decadal prediction large ensemble. And we refer to the CESM DPLE. These are complementing the decadal large ensemble simulations that I showed earlier. Those were not initialized. These are now, we are initializing these simulations with our best estimates of ocean and sea ice states. We still don't do initialization with atmosphere and land model components, and that's what we are currently working on. And just to give you an idea, this is showing essentially summer precipitation in the Sahel region, right here in this box region. We have quite good skill at lead times 3 to 7 years. If you look at the lower right panel first, the black line is the observational precipitation anomaly. The blue line is just uninitialized historical simulation, so there is really not much skill. And the red line is showing our decadal prediction initialized state, and we get quite a good representation or prediction at lead times 3 to 7 years with our decadal prediction system. The top panel shows how many ensemble members you need for robust results for this particular region, and it's region dependent quite a lot actually. So what is shown here is the anomaly correlation coefficient as a function of ensemble size. The blue, solid blue, is our uninitialized large ensemble. The reddish red solid or thick line is the decadal prediction initialized ensemble. So right away, I mean, we have quite a bit of skill right from the get-go, essentially for this decadal predictions. And we can easily beat what the large ensemble does. But another metric that we need to be careful or beat is the persistence, and that's shown by the dashed line here. In order to be able to beat persistence at 95% level, these are the lines, 5 to 95%, we need really 30 ensemble members in this case. And again, this is regional dependent. Some regions, some variables require only maybe 10 ensemble members. But for some other regions and some other variables, even 40 or 50 ensemble members really are not enough. We have data assimilation going on within CESM, and we use data assimilation research testbed for that purpose. In order to, all of these decadal predictions that I mentioned, or our sub-seasonal to seasonal prediction simulations, are initialized with mostly hindcast, ocean, and sea ice states. And we are working towards essentially creating a data assimilation system to obtain ice, ocean, land, and atmosphere initial conditions from a coupled system. A prototype, in this case with DART, that means coupled, fully coupled, strongly coupled data assimilation, meaning that the covariances are essentially, there's a single covariance matrix for all the component models. They are not separated. So everything, a piece of data in the atmospheric model can impact what's happening in the sea ice or ocean immediately. Okay, another partnership that I wanted to talk to you about, and again, the results will be now released, I think, June 8th. We are going to have a press release about this thing. We are collaborating with our Chinese colleagues. That's so-called under the IHASP umbrella. That stands for International Laboratory for High Resolution Earth System Prediction. It's a partnership between Qingdao National Laboratory for Marine Science and Technology, that's QNLM, Texas A&M University, TAMU, and us. The idea is to perform high-resolution ocean and Earth system model development, perform these simulations and also climate predictions, and with the goal of essentially advancing our scientific understanding of interactions among different Earth system components across different space and time scales. And I don't want to preach to the choir. With such high resolution simulations, you can do a lot. You can essentially look at, for example, the role of eddies in decadal climate variability, whether you need to initialize every single eddy to get the sort of improved prediction skill. Or you can look at, for example, how the eddies impact equilibrium climate sensitivity or transient climate response for that matter. So for this purpose, we are using a slightly older version of the model, and for two reasons. That was partly for export compliance reasons, since we are collaborating with China, and also we had more experience with this model version. Atmospheric model and the land model are at quarter degree resolution, and the ocean and sea ice components are at nominal 0.1 degree resolution. I should mention that for this purpose, Chinese ended up recoding pretty much the entire coupled model to run on their Sunway system. These are not Intel chips. These are new chips that China developed, and it's not GPU, it's something in between CPU and GPU. They hired order 100 software engineers to convert the entire code to run on this machine efficiently. And we have now completed quite a big set of simulations. We have completed a 500-year pre-industrial control simulation. We have also completed so far one ensemble member of 1850 to 2100 transient simulation. And we have also completed a bunch of simulations in support of the high-res MIP. That's essentially 1950 to 2050 pre-industrial, 1950 control and 1950 to 2050 transient plus future scenario simulation. And just for eye candy here, we are writing as we speak an overview article summarizing all of these results. This is showing for the 1950 to 2080 period observed tropical cyclones, their paths, tropical cyclone paths, and the categories for tropical cyclones are given here. We have in the Alps, we have about 82 tropical cyclones per year during this time frame. In CESM2 high resolution simulation, we have about 85 tropical cyclones. I mean, and this is not surprising, I guess, in CESM 1 degree, we get fewer tropical cyclones. That's not surprising. If you look at the comparison between the observations in high-res CESM, the intensity of the storms is still less, less than what we see in observations. You can see Alps have more red colors, and this has fewer red colors. And also the latitudinal extent of the tropical cyclone development region seems to be much wider in the 1 degree CESM version, high resolution CESM version than in observations. So with that, I would like to, I don't have any conclusions because I was trying to convey you some of the capabilities and availability of data sets from CESM. As I said, just coming back, many of the CESM versions and all of the data sets pretty much that I showed here are available, and you can either access them through our CSM website or ESGF. The high-res simulations that we are running in China are being transferred to Texas A&M and to NCAR, and they are going to be made available initially next week, next Monday, June 8th, for pre-industrial control simulations, and that can be used for many purposes as well. So, teşekkürler. If you have any questions, I'm happy to take them.